At the end of this alkyne chapter, let's work a little bit on the practices. You have, there are two alkynes are given. This is internal alkyne, internal because the triple bond is inside the molecule. This is a terminal alkyne since the triple bond is at the beginning of the molecule, at the terminal carbon. So in some of these reactions, there should be a difference between the products. We start with the one equivalent of HBr, means don't give it enough HBr to fully saturate. Those partially saturate with HBr, partially saturate the triple bond. This is a Markovnikov reaction. So here, each of these carbons, none of them have any hydrogen. So it doesn't matter where hydrogen and where bromine are attached. So it's one equivalent, so it stops at formation of alkene. For propyne, this carbon has a hydrogen. So Markovnikov reaction will form this product. Hydrogen attaches to this terminal carbon and you will end up having bromine on the second carbon. That's what you will have as the product. Okay. You can put double bond on top or on the bottom, doesn't matter. Bottom is more common. One equivalent of chlorine, you're supposed to add chlorine to just one, so you will have a double bond, and then don't forget it was an anti-addition. It's the same. You will have anti-addition product. The next one is addition of water, but this is Markovnikov and anti, right? So when you add, again, doesn't matter which one of these gets hydrogen, which one gets OH, because they're both the same as far as the hydrogens, and we are adding H and OH. We're adding water in the form of H and OH. So you can say H attaches to this carbon and OH attaches to this carbon, okay? And there's a double bond. And now keto-enol tautomerization happens. Double bond forms here, H disappears, double bond disappears, and H comes here. So this is what happens for this compound. For this compound, Markovnikov matters. You have hydrogens, one hydrogen already, the second hydrogen, double bond, and OH. Okay? Now, double bond appears between carbon and oxygen. Hydrogen disappears, double bond disappears, hydrogen attaches to this. So the octet will be valid on both. Two equivalents of HCl means we have excess, we are fully saturating our bond. If first hydrogen, for the first addition, doesn't matter hydrogen attaches to which carbon. So hydrogen here and chlorine here, right? For the second addition, now this is the first addition. For the second addition, now this is the hydrogen-rich carbon. So you have hydrogen, we are fully saturating, so we have chlorine here. Or you can have two hydrogens here, chlorines here. Either way, that's the same product. For this compound, it matters. You have a hydrogen already, so the first, the first product is this, and then the second product is going to be this. So you have three hydrogens here, two chlorines here. For hydroboration, you have a non-Markovnikov addition. Non-Markovnikov addition, and it's a syn addition, right? H and OH in the syn addition. So doesn't matter, there is no hydrogen priority. So hydrogen here, OH here, and then you have the double bond. double bond disappears here, forms between these, hydrogen disappears here, and it's connected there. So for this one, yeah, it matters. Hydrogen will be added to this carbon, and OH will be added to this carbon. Then double bond disappears here, forms between carbon and oxygen here, hydrogen disappears here and moves to the other carbon. So this is a trade between the two carbons all the time. All right. So you see, for an internal alkene, we end up having a ketone. The keto form is actually a ketone. For the terminal alkyne, the keto form is actually an aldehyde if you want to go with the exact functional group. Last one, with a strong base, we need to deprotonate our alkyne, but here, do we have any hydrogens, any acidic hydrogens in the carbons of triple bond? No, each one has 1, 2, 3, and 4. So there would be no reaction with this internal alkyne. With the terminal alkyne, this is our acidic hydrogen. So let's remove that first and then add it to CH3, CH2Br. So we have CH3, CH2, right? And then we have C, CH3, right? This is what is left from here. So 3 carbons, and 2 carbons here. So this was a good practice on all of these reactions on alkynes. The main reactions you get at this point is how to synthesize. Now you know enough reactions to start synthesizing compounds from different compounds. Synthesis of the chemical compounds. It can be challenging at the beginning, but the key is to know all of the reactions you learned first. For example, the first one is making hept 3-ine from acetylene. So let's learn something here. Acetylene is other name for ethine. Ethine must have 2 carbons, a triple bond, and whatever is left from the octet is for the hydrogens. And we want to change it to 3-heptine or hep3-ine. 1, 2, 3, 4, 5, 6, 7. 1, 2, and 3. So we use a method which is called retrosynthesis. So we work from product towards the reactant. Now let's always compare the reactant and product. In the reactant you have 2 carbons, in the product you have 5 carbons. The only reaction you have learned to increase the length of the chain is to use NaNH2, right? To remove one of these hydrogens and add the rest of the molecule. But you have to pay attention here. If you want to make 7, why is it 5? Hept is 7. From 2, look, this side is this side, right? Correct? So the rest comes from what you add to it. So you have to add a portion from right side. You need to add the portion from left side. And you have 2 hydrogens. So start one by one. When you add NaNH2, you will remove one of the hydrogens, right? So for this one, I do it step by step. For the rest of them, I just do the final product of every 1 or 2 steps. So now we have this. Then on the right side, how many more carbons do we need? 3 more, right? So we add CH3, CH2, CH2, and what should it be? A primary alkyl halide, right? To have an SN2 reaction. So now you see how we use the reactions we learned in synthesis. This carbon is going to attack this carbon and kick chlorine out. So we have H, CH2, CH2, CH3. Now, from 2 carbons we have 1, 2, 3, 4, 5, right? 5 carbons so far. Now, we need to add, now we made this part also. Well, so far we have this part. In order to add this part, how many carbons do we need? 2. And we need to remove this hydrogen. So use another NaNH2, then draw it without the hydrogen. And you need 2 hydrogens, 2 carbons, I'm sorry, CH3, CH2, Cl, another primary alkyl halide. So we will have another SN2 reaction. We have to be careful to take a primary alkyl halide to have an SN2 reaction. Otherwise, we will end up having an A2 reaction. So this carbon is going to attack this carbon and the bond opens on chlorine, and the final product is going to be what we need. So retrosynthesis means going from product towards the reactant by analyzing the difference between the structure of your reactant and your product. First of all, always check the difference between number of your carbons. 2 and 7 means that you need to add to it. How, excuse me, how the only reaction that you have learned so far is to use a base and add a primary alkyl halide. Okay. Let's work on the second example. Preparing butanol from 2 carbon starting material. 2 carbon starting material, the easiest is acetylene or ethine. Ethine, the common name is acetylene. Although the ending is ENE, but it's the common name for an alkyne. We are going to form butanol. Butanol is an aldehyde, CH3, CH2, CH2, COH. You will learn more about aldehydes in organic too. So, one more time, retrosynthesis. Let's compare the number of carbons between these 2 compounds. 2 carbons versus 4 carbons. So for sure we are going to add to our compound. Now, how many carbons do we need to add to this compound? 2. So let's first add NaNH2. So we will have this compound. We need 2 more carbons, so CH3, CH2Cl as a primary alkyl halide. SN2 reaction happens. So we have H, CH2, CH3. Now, the difference between these 2, now we have 4 carbons and 4 carbons in both. Now, the number of carbons are fixed, but the functional group is different. Going from an alkyne to a keto form, to a carbon-oxygen double bond, the carbonyl bond. How? Let's figure it out. You have 2 ways, either using HgSO4 and H2SO4 and water, or add BH3 in H2O2 and base. So let's see which one. If you use this, it's going to be Markovnikov, right? Markovnikov means we add hydrogen here and OH here. So carbon oxygen double bond will fall on the second carbon, but we want it on the first carbon. Means that we need to do a non-Markovnikov addition of water. So BH3 first in THF. At this point you need to know, you're supposed to know the reagents, and then H2O2 in base. So we will end up having C, it's non-Markovnikov, so it's COH, double bond, CH, CH2, CH3, double bond is removed here, forms between carbon and oxygen, and H goes here. Isn't it the same as what we have? Yes, it's just flipped. So that's how you need to analyze it. The other example is find how to change any organic, any hydrocarbon and any other organic or inorganic material to change them to 2-pentanol. So 2-pentanol is this 1, 2, 3, 4, 5. This is 2-pentanol. But the easiest is to grab a 5-carbon hydrocarbon, right? 1, 2, 3, 4, 5. So you can use, when it says anything, you can use alkene or alkyne. The easiest is to grab an alkene. Let's analyze it first. There seems like to be an OH here and hydrogen here. So if we use an oxymercuration with mercury 2 acetate and then NH4, sorry. So we have a Markovnikov addition, means H is going to add here, OH is going to add here. And we don't have any ketone and enol. We don't have a carbon oxygen double bond here, right? Means that we started with an alkene. So that shows how you should be fluent in the reactions you learned. 2 more practices before we finish this chapter. Next one is synthesize 1-pentanol from a hydrocarbon. 1-pentanol. In the previous example we had 2-pentanol. Now we have 1-pentanol. 1, 2, 3, 4, 5. This is the 1-pentanol. And again, it's OH, it's not carbon oxygen double bond. So let's consider a 5 hydrocarbon, which is an alkene. 1, 2, 3, 4, 5. But be careful here how to choose the reagent. If you choose an oxymercuration means if you get the double bond here. If you choose oxymercuration like the previous example, means hydrogen will be added here, OH will be added here. So you will end up having 2-pentanol, what you had in the previous example. You need to have OH here and H here. But which one is more hydrogen rich? This one has 2 hydrogens and this one has 1 hydrogen already, right? So it should be a non-Markovnikov reaction to add OH to a hydrogen poor carbon. Which one was the hydrogen and was the non-Markovnikov? BH3 in THF and H2O2 and OH. And finally, we are going to prepare 2-pentanone. 1, 2, 3, 4, 5. Pentanone means ketone, so ketone functional group is on the second carbon. we are going to make it from any organic or inorganic reagent. You have different options. One of the options that uses some of the reactions that we have used so far is, let's go from acetylene or ethine to this. How? Whenever you deal with an alkyne, you definitely need to have NaNH2. So you have 2 carbons here. How many carbons here? 5 carbons. So you need to add 3 more. This is what you have, right? 3 more carbons in the form of a primary alkyl halide. 1, 2, 3. So it's a primary alkyl halide. We are going with an SN2 reaction. So we have H, C, C, CH2. Don't forget, carbon attacks this carbon. I don't want to see a CH3 here. CH3 means you're violating the octet. CH2, CH2. Sorry, I put CH3 here myself. So 1, 2, 3, 4, 5. The difference between these two is you have a ketone here, but you have an alkyne. If you want to have O here, means you need to have an OH here and H here. Hydrogen-rich carbon gets the hydrogen, so you need to go with H2SO4, H2O, with HgSO4, which is Markovnikov reaction. Hydrogen gets the, you see it's on the hydrogen-rich carbon, OH here. Then with the tautomerization, carbon-oxygen double bond forms here, double bond disappears, and you will have the CH3 there. Okay, so that's how you approach the synthesis questions. We call it retrosynthesis. It's always good, again, to compare the number of carbons and the changes that the reactant is going through to reach to the product. And the key is first to know the reactions well, what happens in each one, what is the mechanism, Markovnikov, non-Markovnikov, scene, anti or SN2 or E2, and then you need to apply them to each step. So it needs a lot of practice. Good luck with that.